Hi, I'm here to convince you that if you were to drop a, well, a large object, let's say a copper sphere of, let's say the density is alpha, and the density is the same all the way through the copper sphere, and the copper sphere has size, well, let's say the diameter is 3 meters, and you also drop from the same height a copper sphere with a diameter, or sorry, this is not the diameter, this is a radius. See, I'm not very good with my terminology apparently. But this also has density equal to alpha. So the density might be, who knows, 2,000 moles per cubic inch, or I don't know how dense copper is, but copper metal of the same density, and you have a sphere which is larger and a sphere which is smaller. Or actually, these wouldn't be, I guess I wouldn't call these spheres, because I think a sphere only defines a surface and not an entire a full three-dimensional space. So it would include all the volume surrounded by the sphere in three-dimensional space. So I guess I would just call that a ball as opposed to a sphere, because I think the word sphere should refer to just the surface of this rather than the entire three-dimensional space or the volume. So my claim is that if you drop both of these from, let's say, an airplane that is way up high in the sky at like 10,000 feet or something like that, there will be a clear, extremely noticeable difference in their fall speeds. And this larger object will hit the ground first. But wait a minute, Tim, are you sure about that? Tim, I thought that all objects, when you drop them, hit the ground at the same time. They fall at the same speed. I mean, I remember there is an experiment, and by the way, I'm just paraphrasing for someone who potentially might be arguing with me. Tim, there's an experiment where somebody actually takes a couple of tubes like this, and they have a feather in one, and that's a pretty bad looking feather. And then they have a rock in the other. Just pretend that's a rock and that's it. Let's just label it feather and rock. And when they dropped these, they both fell at the same time. Yeah, sure. I believe you, actually. In fact, I've seen that for myself. In fact, I wouldn't doubt that there are plenty of situations in which when you drop these two balls right here, they would also hit the ground at the exact same time. But if you drop them from an airplane where there's air friction, they won't. And that's because of their difference in shape. But they're both balls, you might say. Well, I would reply to you that in this case, size matters. In fact, size is considered part of the shape here, which is kind of interesting, but that's how it works. You see, this ball right here is 3 times the radius of this one. However, it is actually 8 times the mass. But it has 4 times the surface area of this one. So, if we compare the ratios of mass of this larger ball to the smaller ball, and the ratio of the surface area of the larger ball to the smaller ball, we'd actually find out that this one has twice the mass per surface area that the small ball would have. And what's funny is I actually have gotten into arguments with people when I was enlisted in the military, when I was basically in between my schooling from computer science and math and computer science, and it was very difficult. In fact, many people did not even come to understand this. In fact, I came up with a very simple way of explaining it just using cubes, and this idea was rejected for a reason that was actually invalid to reject it, because it is actually a valid argument. So if you have a small cube right here that's, let's say it's an inch long and an inch tall and an inch wide, I'll just use a 1 inch like that. Okay, and then you have another one that's bigger, and this cube is actually 2 by 2 by 2, so we're going to use a 2 inch right here, and we're going to compare their surface areas. So how many sides does this cube have? Well, it has 6 sides, so it has 6 square inches. 6 inches squared, right? And this one also has 6 sides, but each side has 4 square inches on it. So what's 6 times 4? 24. 24 inches squared. Okay? Fair enough. So this cube, which is twice both the diameter and the radius, because those are linear, so you can double one and the other one also is doubled. And you actually multiply its surface area by 4. Now, if you were to look at the volume, this would have 1 inch cubed, and this one would have 8 inches cubed. Now this is 4 times greater than this, and this is 8 times greater than that. Now, this is the part of the argument that was actually valid, but was rejected because it sounded like it was a bit strange. So I basically said, well, you could take this cube and you could break it into 8 entities. So basically 8 smaller cubes like this. And we'll just say cube times 8 or whatever. We'll just say cube times 8. So there's 8 cubes here. What is the total surface area? Well, it's 6 times 8. So that's 48 inches squared. But the total volume is actually the same as this one, which is 8 inches cubed. Now you'll notice that the ratios are the same here and here, here and here. Well, duh, because you're just multiplying it by 8 because there's 8 cubes. But basically my argument was that if you dropped this and you dropped this, well, you're actually dropping the same amount of mass and the same amount of volume, but this has more surface area, so it has more air friction presenting to its environment. And if you actually look up the formula for terminal velocity, it is proportional to the surface area of an object, and it is not proportional to the volume or the density. It is related to the mass, but what increases the air friction will be the surface area. So another way you could think about this is with these. If you were to melt down this into smaller balls right here, like this one, you'd get a whole bunch more balls, but you'd have a lot more surface area, and they would fall more slowly when given air friction. And you can verify this with physics professors and people who actually have higher education in physics, and they will tell you the same thing that I told you, which is that given some air friction, the heavier object will in fact fall faster than the lighter or the smaller object in this case. Now, this doesn't mean that just because heavier objects will fall faster than smaller objects when we have some air friction doesn't mean that it's going to be a very obvious thing or a very observable thing in most cases. In fact, if you're just standing somewhere and you're apparently smiling sarcastically and trying to prove me wrong, and you hold maybe like a bowling ball in one hand and a small, let's say, pebble in the other hand, and you drop them, well, I expect to see observably both of them hit the floor about the exact same time. And that's because the forces that are acting on these two objects right here are going to be much greater than the forces in total than the force of just the air friction. So if you were to count the air friction from just dropping this from shoulder height to the ground, the air friction impact on the speed and the actual timing of the object hitting the ground is going to be negligible. So you might notice kind of maybe something will fall more quickly if you were to drop it if there was no air friction whatsoever and it was a very tiny object. Obviously a feather, it's very noticeable. But anything that's dense enough, you're not really going to notice. So that's why I said if you drop it from an airplane, or maybe from a very, very tall tower, you will definitely notice the difference. I hope that, if I need to, in a future video or something, if I need to prove this to somebody, that we'll be able to do an experiment just for fun. And we'll be able to drop a large and a small object of the exact same, otherwise identical shape than their size, and the same density, to prove that the larger one will in fact hit the ground first because it is less affected by the air friction than the smaller object. So that was some physics with Tim, even though I'm not really a physics major. But I thought that was an important topic to kind of bring up in case anybody has an argument about it. And I hope that anyone who disagrees with this will in fact put some comments or put up a challenge so that we can actually proceed with an experiment and prove visually and without any shadow of a doubt that the heavier object will fall faster. Thank you for your time. I will see you guys later.